So the second part of Unit 8 just deals with all of the different ways to traverse arrays. Okay, this time two-dimensional arrays. Uh, our enhanced for loops will be a little bit different, okay, since we're accessing two different pieces. Kind of like first we access the one-dimensional arrays of the matrix, and then we access the values of that particular one-dimensional array. And that's going to be how we'll write enhanced loops. I'll show you some examples in a minute. And then in addition to working with some enhanced loops, we also have this kind of note here: identify, modify, develop algorithms. And it even goes on to say that like all of the standard 1D array algorithms can be applied to two-dimensional array objects, as well as a little note on like sequential linear searches, which we learned about in our previous chapter, Unit 7. But in case you forgot, okay, I pulled up my notes here from 6.4. This is where we learned all of those one-dimensional array algorithms. They mentioned these in Unit 7 for array list, and they're mentioning them again now. So things like minimum and maximum values, definitely going to see that on a matrix. Sum, average, mode. I doubt you'd be asked to find the mode of a matrix, but I can't guarantee it. Boolean returns, like do we have something? Is everything something? Do we have none of something? Sometimes we have to access consecutive pairs, so we have to get a little bit creative in our bounds. Especially a common matrix question is like, is there a matching value above or below? So you have to change the row index -1 +1, and then you have to change the boundaries of your row loop. Or you may have to consider left and right and change the column indexes, maybe even go diagonals. Maybe you take a point in a matrix and look at all 8 of its surrounding values. So you have like the 4 corners, you got above, below, you have left, right. So we could see a lot of variations of this problem. Here's some more Boolean ideas. Okay, like a counter method here. Maybe see a shift. We've seen some variations of that. I'll show you some. Okay. And in terms of reversing the order, this is true maybe with like images that are stored as pixels in like a rectangular grid. You might like invert the image, maybe you'd reflect it across a different axis. So this type of thing does happen in two-dimensional arrays. So anyway, I'm not going to go over every single one of these with you today, but I do want to show you a couple things. So I've made a couple of problems down here at the bottom, and we'll try to write a solution real quickly to each. Now, before we do that, let's just take a look at an example of like an enhanced loop structure. So I set up a little method down below to actually, one's going to generate a matrix for you, and one's going to print it. So I showed you some ways yesterday to print matrices. I just wrote a little method today that could print. So if we want to get a visual look at our matrix, we can just call this local print method that I made. And I made another method here called make matrix. You tell it how big you want the matrix to be, rows and columns, and then it will generate a matrix for you, okay, with some random numbers. So right now, if I run this little bit of code that I have, I've called these methods a few times. And right here, I wanted to give you an example of my enhanced loops. Okay, so right here, I made a 3x2 matrix, 3 rows, 2 columns, and I printed it. And that's what you're looking at right here. And then I went ahead and did a sum method, just so you could see like a quick example of how enhanced loops work. All right, so this is a little strange, but what this is doing is, this is acknowledging the fact that a two-dimensional array is made up of one-dimensional arrays, right? This particular two-dimensional array has 3 one-dimensional arrays, okay? They are visually row 0, row 1, and row 2. The 6, 3 for me would be my row 0, the 8, 7 would be row 1, and the 2, 2 would be row 2. And they're indexed 0, 1, and 2. But I'm not using indexes today, okay? Unlike what we did in the earlier lesson, these aren't indexed. This is an enhanced loop. So row will hold each one-dimensional array of matrix, okay? If matrix had 1,000 different rows, then that variable row would hold all of them, not at the same time, right? takes the first one and then the second one and so on. It always goes in order. So it's going to start with the one found at index 0. That's the top. And then just below that, row 1, index 2, and so on. Okay. When you grab a row from a matrix, you're grabbing a one-dimensional array. This is the enhanced loop that we learned to write in Unit 6 for one-dimensional arrays. So capitalizing on the fact that row is a one-dimensional array, I can access all of its individual values. This particular matrix holds integers. So I've declared my 1D arrays and my values as ints. If I had a matrix of strings, I would change both of these int references to be string. If it was students or some user-defined object, I would use that variable type. It'll work for anything, okay? But this will grab all of the values from the row. First up would be the row 0. It has a 6 and a 3. That means this loop would iterate twice. And on the first iteration of the loop, val would be 6. And on the second iteration of the loop, val would be 3. That would conclude the first time through. Okay. And then row at that point would take on a new value. Okay. Row would become the 8 and the 7 found in row 1. So val would be 8 and followed by val 7. Okay. That would conclude that pass of the loop. Then we'd go again. Val would take on the 2. Finally, val would take on the 2. Ultimately, val is going to see every value of the matrix, and they're all going to get added onto that sum. 9 plus 15 plus 4 makes 28. That's where that 28 came from. I didn't put it there. Okay? This is all randomly generated. So if I hit run again, I'll get a different 3x2 matrix. I'll get different values. This time I got 38. You could change this here. You could say I'd like a 4x7 matrix. And now you're going to get 4 rows, each holding 7 numbers. And if we added up all 28 of those numbers, apparently we'd get 125. Okay. And so this is an example of a nested loop. Now, what's interesting is within this nested loop, you could even get more creative. So for example, I don't necessarily need to have both of these as enhanced loops. I could write here like an indexed loop to go across that particular row, acknowledging the fact that row is a one-dimensional array. I could write something like this. Now, what I'm saying is I want to go into row, okay? And I know that it's a one-dimensional array, and I is going to produce all of those indexes. Let's put the numbers back a little bit smaller so we can kind of do a quicker visual check to see if the addition's working, if we're truly accessing all of the values. And all right, so 1, 5, 6, 1, 7, 5, 12, and 13. Yep, that worked. What that did was it grabbed the row 1, 5, 6, and then it grabbed row's index 0 value, which is 1, row's index 1 value, which was 5, and then it grabbed row's index 2 value, which was 6. That ended the first pass. Then it grabbed the next row and went through the same process, a 1 and a 7 and a 5. Okay. Or, we could get even crazier. We could try to do like, an index loop on the outside followed by an enhanced loop on the inside. Okay. That would look something like this. So here I would say like, give me all of the indexes that belong to the matrix. So like this would be matrix.length. That's, in other words, how many rows there are. And then once you give me that index, I could say, all right, now give me the value found in the matrix at that particular row. Okay. So matrix with one dimensional just grabs one of the arrays in the matrix. So at this point, I would actually be back to saying sum plus equal to val. Val is going to take turns holding all of the values that come out of the matrix. So again, let's see, we got 9 and 4, 13 and 16. Yep, 29. It accessed every number. you don't need to do all this different stuff, right? Remember, you can write loops however you want, but there's a chance the College Board might throw some stuff like that at you. So you should just understand that, like in these cases, we are writing correct loop code. All right, let's take a look at these methods down here and see if we can solve them. All right, you want to find the average of all the values. Okay, no different than before. We want to go ahead and get some sort of double. Maybe you want to call it sum. Okay, and you want to loop across all of the values of Matt. Now, if you want to do that in an enhanced loop, you're going to say, give me a one-dimensional array from the matrix, followed by give me a value from that one-dimensional array. And then your sum will simply increase by all of those values, and you'll get a total sum. Here's the little trick. How do I know how many values there were? Previously, I would have said mat.length. That won't work today because that's just the number of rows. But since it is a rectangle, I could say multiply that by the number of columns. And again, notice how I use zero. Zero is like your safest bet. You know there's going to be a row there, or else it's not really a matrix. Very often in AP questions, they'll say like, precondition, Matt has at least one row. All right. And they might even say has at least one column also. All right. And so these are the numbers. I'm a little too lazy to add that up and take the average, but 5.3 seems reasonable. Okay. All right. How could we get the min value? Well, previously, if we were doing a min value problem, what we would have done is we would have said like, all right, give me the first value from the matrix as like our starting point. Well, remember, the matrix is doubly subscripted. So mat 0, that's actually an array. If I ran this right now, I'd get an error for a mismatch. I need to subscript it twice. That's the first value of the matrix. Okay. Then what I'll do is I'll go to every other value. Now, you could do this with enhanced loops like I just did, or you could do it with, with an index loop. I think I'll just go ahead and grab these loops here to save us a little bit of time. Okay. And then I'm just going to ask a question. All right. Is this value that you just took out of the matrix smaller than what I thought was the minimum? Because if it is, that means I was wrong and there's a better value. And in the end, I should have the minimum value. All right. Yeah. Minimum value of 1. That seems reasonable. All right. Is there an 8 in column 2? Okay. Well, for me, this time it should have said false, but another time if I write it, I might get true. Now, like I said here, try to only write one loop. And the reason I'm saying that is we shouldn't write a loop to generate column indexes if we already know that the column index is 2. So I'm just going to write a loop that generates row indexes. And I'm just going to walk across the matrix. Remember, if you want the length of the matrix, okay, that's the number of rows in it. And we'll just take every single row that belongs to the matrix. Okay, I'm not going to write a second loop because I already know that I will be accessing this matrix at column 2. So I'm just going to put a 2 in there. If I get an 8, then I don't really need to do anything else. I'm done. I'll just simply return true. I definitely don't want to say else, right? That would be poor logic. I only want the loop to look for true cases. If I make it all the way through column 2 and I never find an 8, then my backup plan is false. But definitely don't write an if else here because you would only be looking at one number and you'd be making up your mind before you looked at any others. My column 8 this time actually did have, my column 2 actually did have an 8 in it. That's why I got true. If I run it again, maybe I won't see an 8 there and I might get false. So this time I got false. All right, return all values of column 2. I don't think I want the word the there. I'm speaking like Starfire. All right, so public static int get column 2 int mat. All right, return all values of column 2 as a 1D int array. Now, we don't have a 1D int array, not yet, okay? So maybe the first thing you want to do is make that I'll call it call2. And here's the thing, when you make a new array, you've got to put a dimension in it. What's the dimension going to be? Let's see. Well, look at my column 2 here. Okay, it had 3 different values in it. Now, how would I have known that? If they just hand me any matrix, how would I know how many values would be in a particular column? Well, the number of rows is what holds the secret here. So we'll actually use the number of rows to be the dimension of this column array, because a column has as many values in it as there are rows. Okay, so now I've got this set up. I know that the column is 2, so I'm only going to write one loop. This one loop that I'm going to write is going to go across all of the row values. So like I did a second ago, mat.length, okay, r++. And then what I'll do is I'm going to put into column 2, okay, I can actually reuse this r index because I want to start at 0. And I'm going to go into the matrix. I'm going to use this row index and 2. The matrix needs 2 subscripts. I know one of those subscripts is 2 because it was told to me. I'm generating all of the row subscripts. If there was 100 rows, this would run from 0 to 99. And if there was 100 rows, then there would be 100 values in column 2. Okay, so we're just going through and doing all of them. All right, and eventually we'll have column 2 all filled, and we'll go ahead and return it as a one-dimensional array because that was the return type of the method. And I did a little print cheat here, but it printed out the array nicely for us, and it's 959. Now, that it showed up this way, but watch this. If I go up to here in my tester, and let's say I change this to be 7 rows of 8 columns, and I run it again, well, my method won't care. It will adapt to these new numbers. I didn't write anything dependent on those numbers. And so now column 2's got more values in it, 2, 7 down to 1, 5. And my code adjusted. It went in and it got all 7 of those values from row 2. From column 2. If you made a matrix that didn't have at least 3 columns, you'd get an out of bounds error. So we're kind of dependent on that here, but okay, this is working just fine. And then finally, adjacent equal values. Return true if there's 2 equal values in mat found next to each other in the same row, false otherwise. Now, in this problem, I want to access every single row, okay, and give them all a chance. However, I'm going to have to be careful as which column indexes I access. So I don't think I'm going to use enhanced loops here because I kind of want to see the indexes as they're being produced. All right, so I've got my row indexes handled. If I just wrote a similar loop for columns, it might not work so well. Let's think about why that is. Now, remember, when you're writing a column index loop, you have to pick a row and then say, okay, I want all of the indexes out of that particular row. That's how many columns there are. And now, if I said something like this, and now I go into the matrix at that row, at that column, if it's equal, let's do the value to the left, let's say. Okay, if you wanted the value to the left, you'd stay in the same row, but the column would be smaller. So if you're in like row, like for example, like this 4 right here is at row 1, column 4. It matches this 4 here. That's in row 1, column 3. So I dropped the column index to see that number. But like we've seen before, if you're going to drop that column index, then you better start your loop at index 1 so that you never travel to column -1. So like we've seen before, when you start messing with indexes of one-dimensional arrays or an array list, now we're doing it in a two-dimensional array, there's that potential for going out of bounds as you start moving left or right. If I had put C +1 right here, totally fine, right? I would still start at 0 then, and I'd probably want to back this up 1 so that I didn't quite reach the last column. Now I'd stop at the second to last column, which would make it safe for me to look 1 more to the right. If I find this case, I'll immediately return true. However, if I make it through all the values and I never find it, then I'll return false. I've got a pretty big matrix generated right now. It's probably going to say true, and it did. And let's see, for example, I should be able to find it quickly. Like here's two fives. Okay. If I went back, I think earlier, I don't remember now because I changed it. I think this was a 3x4 or 3x5 earlier. So more likely that we would see a false here, but we still might see true. It's all luck. Okay, we don't really know what's going to happen. So I got another true. There was two fives. There was two ones. Okay, and you could run it a couple times just to see if you're getting the right values. I got true again. There's a couple of sixes next to each other. Okay. Anyway, I think it's going to work. You can trust me on it. But it's not going out of bounds. We're accessing all the values. This time we got false. There weren't any adjacent equal values here. Okay. There's multiple fives. There's multiple twos, but they're not next to each other.